Hello and welcome to the first session of our Biomedical Engineering workshop by SimScale in collaboration with Medical School of Hannover. Yes, I'm very happy to see so many people who have joined our first session today, and before we actually start to dive into our today's topic, I would just like to make sure that the audio is working for everyone fine. So guys, you will find a button in the control panel of the software we're using for this webinar, which is called Raise Your Hand. And in the case you can hear me loud and clearly, please press this button so that I know everything is working fine. Great, I already see some hands, so it seems finally that everything is working. In the case, for some reason, I don't know exactly why, the audio should drop for you. You have also the possibility to use our toll-free audio service number to join the audio stream of this webinar. So just dial one of these toll-free numbers and access this code. By the way, we will record this webinar, so you will be able in any case to watch the recording afterwards. Okay, great. Then yes, I would say let's get started. First of all, let's take a look at our today's agenda. So at the beginning, I will give you a crisp introduction into the idea of this workshop and what the idea of this webinar today is. After that, you will receive a first crisp introduction to biomedical engineering. So we will talk about the question what biomedical engineering basically is, and also how simulation can help in this area. Just after that, you will get an introduction to the idea of engineering simulation. We'll also show you how to use the SimScale platform to perform your own simulations, and after that we will take a look at a hip joint prosthesis simulation. I will show you a homework which you can do. It's faculty, but it can help you to qualify for free training, and after that we will have time for question and answers. If you have a question in the meantime, just write it in this question chat box, and I will collect all the questions and answer them as soon as possible. Well, let's first of all start about the idea of this webinar. And first of all, maybe give me the chance to introduce myself. My name is Milad. I'm working at SimScale as a academic program manager, so I am responsible for our collaboration with universities and academic institutions, and I also keep care for sure for organizing this workshop series and also to create new ways and environments how we can teach people to use simulation. I have, by the way, a mechanical engineering background and also were involved during my studies in biomedical engineering myself. And first of all, what is this workshop about? So you all joined this workshop series, so I think you basically know what we will do in the next 3 weeks, but let's just put it again into a nutshell. As you know, there are a lot of people who are really fascinated about biomedical engineering, and on the other hand, there are also a lot of people who are fascinated by simulation, and both industries or both subjects, biomedical engineering as well as simulation, will be very important in the future. The idea of this workshop is to give interested biomedical engineers and interested students and hobbyists first insights into engineering fundamentals, and especially helps them to get first hands-on experience with simulation. What does it mean? Really, the idea of this workshop is that after joining all 3 sessions and submitting the homework, you will really have a basic idea of what is simulation, and you will be able to use these tools we show you for your own projects related to biomedical engineering. Therefore, this workshop is really hands-on, and it's not so much focused on, let's say, math, physics, anatomy, or simulation theory. So we will not talk a lot about the mathematical models in the background. But if you're interested in this, there are a lot of good books I can recommend. After this session, I will also send around or post a list with external reference you can take a look at if you're interested in something special. And so in the case you want to learn also a lot about the theory of simulation, this is not really maybe the perfect training for you, but nevertheless you should join We will talk also about that. And by the way, you can qualify for free professional training by submitting all these 3 homeworks. So, and then you will win a free professional training. And last but not least, because a lot of people ask that, why we're doing this workshop. And to put it, or to make it short, we want to make simulation a standard technology for every engineer in the world, and therefore a part of our mission is also to show every engineer in the world about the potential of engineering simulation. And we really want just to introduce some interested engineers to simulation and SimScale, and for sure we would love to get product feedback from you and contributions to our simulation library, which I will show you later. Okay, now let's talk about how it works. We have, as you know, 3 one-hour online sessions with live demos. This is the first one, and we will have the next one next week, same time. In every webinar session, we will talk about some fundamental knowledge you know, and afterwards I will show you how to use this knowledge to set up yourself a simulation example from the field of biomedical engineering. After the session, you are able to do the simulation on yourself, to perform it on your own user account. We will provide you for that also with a tutorial, and submitting all 3 homeworks by using a form we provide will qualify you for a free professional training, the value of €500, as well as certification of a certificate of participation. And since there were a lot of questions, I would just like to talk about those ones who were really asked a lot. So first of all, a lot of people wanted to know if the workshop is recorded in the case they miss it. And yes, we are recording all this workshop session, webinar sessions, and you will be able to access them from tomorrow on our website and our YouTube channel. Please don't start to simulate during the workshops, this webinar, or during the webinar. The webinar is really about showing you something, about interaction. It's the best possibility for you to ask questions. Therefore you should really wait and start with your simulation after the session. You can simulate yourself using our SimScale platform, which is absolutely for free. It's web-based. I will show it to you later, so you don't need to install any software or you don't need any dedicated hardware. And if you have any troubles with setting up your simulation of the homework, if you have general questions, we have a forum with a dedicated section in the forum where you can discuss all these questions, where you will get immediately help. Okay, and now I think it's time to really dive into our today's topic. So let's do the introduction to biomedical engineering. But before I start, I would just like to make a short poll, because I also want to know who is in this course today. And first of all, I would just like to know what your educational professional background is. So you will see right now the poll is opening on your screens, and you have, in the end, we have 5 things you can say. So engineers, medical students, natural scientists, and a lot of people are answering the poll. So come on guys, 60% already answered. Okay, and looks quite interesting. So the result of our poll is so far that 35% of the participants today are engineers, 55% are biomedical engineers or dedicated engineers for biomedical applications. And we also have some medical students, natural science students, and even people who have a completely different background. And that's really a great thing. And this really shows in the idea of biomedical engineering, because during this workshop you will be able to join forces between different professionalities, and especially with the forum I hope we will see some good discussions. So I think there will be a lot of aspects where maybe people with a medical background or biological background know more. There will be other aspects where you need an engineering background to understand it very good, and so I think that's a really good situation. But now let's start. And I mean, since half of the audience is studying biomedical engineering, this is maybe not new to them, but I think for people who never were in touch with biomedical engineering before, this could be very helpful. And let's start. First of all, biomedical engineering is nothing you can define so strictly, because right now I know about 5 different definitions for biomedical engineering. But there is a definition which is used a lot of times, especially in English books, which I like very much. And it's basically, it says that biomedical engineering is the application in the end of advanced knowledge in engineering, biology, and medicine, and it improves human health through cross-disciplinary activities that are integrating the engineering science with the biomedical science in clinical practice. So, I mean, this is a definition, and I'm not a big fan, you know, of learning definitions, because they are written in books, so you don't need to know them completely. But in the end, this rough definition is giving us showing two very important aspects of biomedical engineering. So in the end, biomedical engineering is it's about cross-disciplinary activities where you join knowledge in engineering, biology, and medicine. And the aim of this is to improve human health. And there are basically two things, or two, let's say, directions where biomedical engineering can go to. First of all, you can use biomedical engineering or technologies related to biomedical engineering to understand living system. Let me give you a very easy example. X-ray. X-ray was designed by physicians, or the idea, the idea of X-ray device is from a physician. Engineers then built these X-ray devices, and these X-ray devices helped a lot, especially in the past 100 years, to understand the living system, because it was the first time you were able to look into a living system. And let's say another aspect is that based on this knowledge, you can develop devices, algorithms, processes, or systems that advance medicine. And a good example for this is the hip joint prosthesis, which we will take a look at later on. And as I mentioned, there is not only one definition of BME, and therefore BME had a very broad variation of different areas. And this, for sure, I just made a kind of list. So if we would say and try to divide biomedical engineering in different areas, for sure everybody would have another kind of diagram here. So, and therefore this is just 6 examples of areas I took. There are even more. But let's just take a look at these basic areas. And then we have something like biomechanics, biomaterials, clinical engineering, tissue engineering, medical imaging, and bioinstrumentation. And all of them, in the end, are referring to different things. For example, biomechanics is really, let's say, related to what we're doing today. It's about using the knowledge you have of engineering and mechanics and apply it to the human body, for example, in order to design for prostheses, etc. Biomaterials is not about the mechanics, but it's about the materials which are used. For example, when you're going to design a prosthesis, there are different criteria it has to fulfill. One, for example, is quite obvious. The strength or the material properties of this material, it must be strong enough for all the stress which is occurring. On the other hand, it also needs to be non-toxic. And then we have other areas like tissue engineering, which is about, in the end, how to create or make artificial tissue. Here's a very good example. I think they added some cells of the ear on a mice, and then after some weeks you had this artificial ear on the mouse. And for example, you have medical imaging, which is about the technologies of, you know, X-ray devices, MRI devices, and for every of these areas you need different kind of know-how. For example, for tissue engineering you need to know a lot about biology, about the physiology of cells. So here you, for example, also need a lot of biologists. While biomechanics is mainly really about applied engineering science. And what I want to say in the end that for sure biomedical engineering is a very big area of interest, and therefore maybe what we show you today you would think, how can I apply it to what I am doing? But in the end there are two ways of apply simulation to this. You can apply it directly to simulate, for example, how you have to design something that it fulfills the physical principle of what it should do. For example, if you have a X-ray device, you have to design it on a physical way that you have this X-ray radiation, but you can also use simulation to optimize something other on this device, for example, the cooling of the X-ray device. And yes, and I mean, now this was very, let's say, theoretically defining things. Let's now take really a look at what biomedical engineering means for our daily life. And for example, let's just take a look at 10 different milestones in biomedical engineering. These are all devices which were developed in the past and really helped to push the boundary of medical healthcare. First one is very easy, the thermometer. It was invented 1603 by Galileo Galilei, and the first one was, this very easy one where you had this different liquids with different densities in this tube here, and then depending on the temperature of the water, which was equivalent to the temperature of the system, you could understand you can see or calculate the temperature based on the position of the head of these different fluids. Or X-ray, which I talked about, was basically invented in the end of 19th century by German researcher Röntgen, but it took like 10-15 years until the first commercial X-ray device was manufactured for medical use. Or for example, the iron lung. If you have, for example, a disease of your lung, sometimes you need an external lung. And this iron lung was the first device made it possible to treat people who had really bad lung diseases. Or if we go further, for example, dialysis. If you have problems with your kidney, you need an external device to clean your blood. And all these great things were invented and are good examples for biomedical engineering. And some of them have other approach than the others. For example, the prosthesis, it's directly implemented into your body. So there we are doing engineering, we are designing parts of the body. In contrast to that, X-ray will never touch physically your body. So X-ray is a good example for a device we use in X-ray is a good example of a device which is used by physicians, and a prosthesis is a good example for a device which is used in the body of a person. And during this workshop series, we will take a look at 3 example applications of biomedical engineering. We will take a look at a prosthesis. We will take a look at a stand, which is a device to stabilize vessels, and we will take a look at blood flow. And all these areas, or all these 3 examples, prostheses, heart valves, and stents, really change the life quality of people. And they were all made possible by a combination of engineering, medical science, and all of these 3 things can be simulated, and simulation easily shows you how to improve them, and it will also show you how these devices are working on a physical perspective. Okay, guys. There's already a first question by Niveta, and he wants to know what are the implementable device found till date. And that's a very good question. I would like to answer a lot of the questions related to biomedical engineering right now. So if you have questions, please write them Yes, write them right now. And yes, I would like to come back to the question. So you're using different implants, as I said. The basic other examples we have today are for shoulder prosthesis. We have artificial heart valves. We have artificial vessels. So there are a lot of implants and prostheses found today. Okay, I hope that asked your question, because I think there are like 10, 20 different implants which are already available today, and I cannot name all of them, but heart valve, shoulder, hip joint are all good examples where implants and prostheses are used. Great. Okay. Next thing we'll talk about are the fundamentals of simulation. So right now I try to show you what biomedical engineering is, and now let's talk a little bit about what simulation is, or engineering simulation, and how we can use it for biomedical engineering. Just because some people are asking, for sure there are a lot of other devices like a pacemaker which also would fall into implant category. I just wanted to point out that there are a lot of implants available today, but I cannot name all of them right now since I'm not a medical engineer. Okay, and before we start to discuss about fundamentals of simulation, I've prepared a second short poll, and it's just to get to know about your current experience with simulation. So I've opened a new poll, and you have 4 options. And I would just like to know what are your expectations and what you really want to learn about simulation. Come on, guys. 70% already voted. Okay, and it looks like most of you have a little bit of experience of a simulation. 40%, 35% have some first experience, 35% know what simulation is but never used it, and 10% never heard about it before or say they are an expert for simulation. Okay, great. Also here we have a lot of different backgrounds and a lot of different experiences, and this can only be an advantage in the future. So let's start with simulation and make it very crisp. What is simulation? Engineering simulation is in the end about technologies which allow you to perform virtual tests. And why that can help will be very obvious after this short example. Just imagine you're working at a medical company, and your company is developing external global valves. And now it's your job to completely design with your team a new valve. And the standard design process is like that. You would start with some list of requirements, and then you would really start to design a first prototype. That means you would design every part of this prototype. Basically, you just want a device and you to control a volume flow, but you have to design every single part. The valve body itself, all the screws, the sealings, the electromechanical control components, and this takes a lot of time. And after a lot of investment, you are able to build a physical prototype, test it, and then to do a design check to optimize your product. And this is very time consuming, costs a lot of money, and is a very slow process. Simulation, also called CAE, allows you to direct perform virtual experiment from your virtual design. So you can directly create a simulation of your computer-aided design model. And this allows you to perform very early, fast, and cheap cycles. And the reason is quite obvious. I mean, if, for example, we go back to this example of the valve, instead of designing first of all the whole valve with all screws and sealings, we would just design the main body of the valve, so the valve body and this tube, and first of all just optimize, let's say, the design of the valve body. And then we are able to optimize it in a very early stage, and we are also able to test it every time we change something. And that allows us really to design with simulation products better, faster, and cheaper. And this idea, you can also apply it for sure on every other product of biomedical engineering or any other product in general. So simulation is a very powerful tool to take early design decisions and allows you to make virtual experiments. And you will now ask yourself, okay, it sounds like a good deal, but if it's such a great thing, why is only a fraction of engineers even using simulation? And the reason is that simulation traditionally was very expensive and complex to manage, because the software you needed was very expensive. You also needed dedicated hardware, very high performance computing system, because this simulations came with a lot of computational effort. And therefore, the costs were very high. You needed a lot of know-how to use the tools, and you needed to take a high entry investment. And maybe that's a point to introduce our company a little bit better. What we are doing from SimScale, we have developed the first browser-based simulation platform, which means instead of installing locally software, you can access our 3D simulation platform via your standard web browser through the internet. You can perform all your analysis in 3D in your web browser, and all computations will be done in the cloud. And this, first of all, is the world's very first end-to-end CAE workflow, which works completely in a web browser. So you have a leading-edge simulation tool available in your web browser. Next, SimScale is more than just a tool. It also brings together content and people. We have a simulation library, which I will show you later on, where you can easily import thousands of ready-to-use simulation projects to your own workspace. And SimScale also brings together people like you all joining our session today. And so you can directly get in touch with them, discuss with them, and it's a really great thing. And let's just take a look at some features of SimScale. First of all, we have our so-called public projects, which you can find very easily. So when you go on simscale.com, you can create a free account here, and you can then access, for example, on the community, our public projects. So here, for example, you can see, and all these projects are 3D simulation projects, which you can access very easily. Let's take, for example, this front wing. And you can browse through all these public projects and import them with one click to your workspace. But beside of this, we have a lot of more great things. We have a forum, which you will also find here. And in this forum, we have even created a dedicated category on the SimScale workshops, Biomedical workshop, which is really only for our workshop series. There you will find all the tutorials for the homework assignment, and there you can ask all your questions. And we have also for a lot of other stuff forum categories. So if you have general questions about simulation, or a question about SimScale, or if you want to give product feedback, yes, you can do it there. And we also have other great things. For example, I don't want to talk too much about that, but we have also a blog you can access. With a lot of fun, great news you will find there. We have a lot of other tutorials, and we even have professional training, which you can qualify for free. Great. So I think you basically understand what SimScale is and what simulation engineering is. And now I would say it's time to start with our actual topic today. Let's talk about hip joint prostheses and how we can use simulation to optimize them. And first of all, maybe let's start to talk about the hip joint. Here you can see an image showing the anatomy of the bones of your skeleton, and you can see exactly here your hip joint. So this here is our hip joint, and basically the hip joint in the end allows movement of the legs and therefore stabilization of the whole body. And in the end, you know, it's really like you have this head, and if you look at the components, more in detail, you can see what it's made of. You have this femoral head, which is in the end part of the bone, and you have the acetabulum and the femur. These three parts: acetabulum, femur, femoral head, and femur. And in the end, this femur bone, has on the femoral head, you also have a very thin layer of cartilage, which is called the acetabular labrum. And this layer is, on the one hand, it allows, reduces the friction. On the other hand, it's also limiting the degrees of freedom. So you have in total 3 degrees of freedom for this, for your hip, and they are limited by the structure of the cartilage on the femoral head. And you can imagine if you now have damage in this cartilage layer, your hip joint will not work properly anymore. But before we talk about that, let's just take a look at the structure of the femur bone. So if you would make a cut here and take a look, you would see that the femur is made in the end of 3 components. And the first outer component is so-called cortical bone, and it includes sublayers like peri, mid, endo, and this cortical bone in the end is the outer skin of the bone. And inside of this cortical bone you have the trabecular bone, and the trabecular bone will become very important later. And it's made of let's say of a dedicated structure here. And inside we have the bone marrow, or when we have a hip joint prosthesis, the implant, the shaft of the implant. And this trabecular bone has some very dedicated properties, and which is called mechanotransduction. And to understand this, you have to know that your this trabecular bone includes the trabecle, very small structure, and this structure can orientate in the direction of principal stresses. So in the end, what is happening, you have inside the bone, you have this trabecular structure, and then because of the stresses going through the bone, the trabecular bone is orientating in that direction, which in the end means that in everywhere where you have high principal stress, you will get the density of the bone will become higher, and in areas where you have no principal stress but shear stresses, the trabecular will disappear. The bone will there become or have a less density. And this is a very important effect you really have to keep in mind, which will become also very important when we are going to talk about the way you design a prosthesis. And now let's imagine what happens. When you become older, and for some reason, let's say you have a damaged a femur head, then it's necessary to replace this joint by an artificial joint with a hip joint prosthesis. The prostheses are looking generally like this. So you have an implant, which is going into the femur bone. On this implant, you have a new artificial head. And both of these things are going inside to the bone. And so you are replacing this biological joint by this mechanical joint. And this effect of Wolff, which I told you about on the last slide, which is saying that trabecles are orientating in the direction of principal stress, has a very big impact on the structure of the femur bone. And what is happening now is, when you have a different material mix, for example, in your hip joint, because you're using an implant, then the implant is, when it's made, for example, out of steel, it is much more stiffer than the bone. And everybody who was involved in the mechanic or knows a little bit about the mechanic of composite materials knows that if you have a mix of two materials, let's say the one with the higher, which is stronger, will take most of the stress. And what is happening in the end, you can see it now, if you have a natural hip joint, the body stress will distribute on both legs and the whole bone structure symmetrically. But if you have on one side, for example, now an implant or a prosthesis, which is much stronger than the bone, or stiffer is the right word, much stiffer than the bone, it will happen that most of the body stress is transferred through the leg where you have the implant. And that will have two effects. First effect is that the bone structure around the implant will become weak, because it's not transferring anymore a lot of stress. So there is a big risk that, for example, the implant itself will not stay correctly in the bone. The other problem is that the whole skeleton under this prosthesis will also become weak, and the density of the bones will go down because of the stress fielding effect. And that's a big issue when it goes to design hip joint prostheses, because on the one hand, you have to replace mechanical parts, so you need somehow you need stiffness, and on the other hand, if it's too stiff, it will have a negative impact. So, and this is, for example, something which was a bigger problem like 20, 30 years ago. The first prostheses were made of steel, which was much too stiff, and then people really get prompted after 1 or 2 years they had to open the whole bone again and replace the outer structure of the bone, because now this was damaged. And if there are no questions related to the hip joint prosthesis, let's now really take a look at what we will do right now. We will right now simulate such a hip joint prosthesis, which is made like this. You can see the different components. So we will use a 3D CAD model, including the hip joint head, the hip joint stem, which you can see here, the stem, this is the head. And then we also have the trabecular bone, here it's in brown, the outer cortical bone, and the inner bone marrow. And we have a system now of, in the end, 5 different parts made of 5 different materials. We have the head made from cobalt chrome. We have the femoral stem made of a titanium aluminium alloy. We have the coracal bone, which is our own material. We have the trabecular bone, which is also made of, and we have the bone marrow. And here you can see, by the way, all the different mechanical properties. We have 2 things. We have the Young's module and the Poisson ratio, which is used to describe a linear material model. And the Young modules, in the end, is nothing more than, let's say, a stiffness for linear elongation of the material, and the Poisson ratio describing how this is working, how the thickness of the material is changing, for example, when it's elongated. And we can describe all materials, all linear materials on our simulation based on the Young's modulus, the Poisson ratio, and the density of the material. And we will now create a simulation where we fixate, like it's in reality, this lower part of the bone, and then we put two loads, one load on the hip joint head and one load in the other direction on the trabecular bone. And this both two forces, by the way, were calculated based on what we know about the kinematic of human walking. And what we will do right now, we will simulate how for this given load case, so walking with 1 kilometer per hour, the stress will distribute inside of this hip joint prosthesis. And the good thing is it will not only tell us if the design is strong enough and how much it will, for example, bend, but it will also give us insights about the stress distribution inside the bone and therefore about the risk of stress shielding. And yes, now let's really start with the simulation. First of all, let's take at the process. And this is a general process, by the way. And first of all, for every simulation, you need a 3D-dimensional model, a so-called CAD model. And this CAD model is first of all imported to your simulation tool, and then you have to do something called pre-processing, which means the following. The final design sometimes has a lot of details which are not necessarily important for the simulation. To give you a very easy example, just imagine something completely different. You have an airplane and you want to do a fluid aerodynamic simulation of this plane. Then you have, like, let's say 20,000 screws on the skin of the surface, but the screws are so small that they will not really affect the overall physics of this phenomena. So you have to minimize your model as much as possible. And after you've minimized your model, the next process, which is also part of pre-processing, is called the so-called meshing, which you can see here. And yet what basically happens is you're dividing your existing model into a lot of small cells. And the reason is that we're still working with computers, and all the equations we're using for calculate stress, etc., are not analytic equations. So the equations we can only solve numerically. And in the end, what you can see here is the local resolution of a simulation. So for every cell, we will calculate the stress. And so with dividing your model and the smaller submodels and the smaller cells, you are in the end telling the computer where you want to have let's say, more finer result and where a coarse result is good enough. And the last step is to analyze the results and to take a design decision, which we call post-processing. And let's really start directly with the pre-processing. And I have already prepared something. So here's a project. And by the way, everything I'm doing right now, it's in the web browser, as you can see here. So later on I will share this project with all of you so you can import it to your own workspace. And then you can start to set up the simulation here. Okay. And here we go. First of all, let's just take a look at the structure of the SimScale platform. So we basically have this ribbon bar here, which is guiding you through the whole simulation process, from the mesh creation to the simulation setup and even the post-processing. Then you also have this project tree on the left side, which is giving you the structure you have to follow to perform all necessary steps. And this project only contains the geometry of the bone with the prosthesis. So let's take a look at the geometry first. You can even also import your own geometries by the way. And what we can see here is first of all are the dimensions in all directions. And this makes sense. So it seems that we have a bounding box diagonal length of nearly 0.3 meter. So it seems that the scaling of the model is right. And if we now take a look at the model, it's made out of different solid bodies. So we have, let's maybe start with the solid 4. This is the hip joint head, which is dark gray. Here in green, we have the stem, the hip joint stem. And if we take a look inside, you can see the different parts of the bone. So this outer part is the cortical bone, this brown part, and then we have the trabecular bone, which is this blue stuff, and we have the bone marrow, which is represented, sorry, other way around. We have the bone marrow, which is blue, and we have the gray trabecular bone. And right now we will divide this geometry into small cells to have a computational mesh to perform the simulation. Because you should not forget, later on, the simulation tool is only calculating quantities like stress, forces, and displacement for these cells. And first of all, we create a new mesh project. And then we have to choose the base geometry. And we have only one geometry. We want a mesh based on the hip joint prosthesis. Then we can add mesh operations, and you see a lot of different possibilities you have. The lower 4, you can use them for structural simulations. The upper 4, the lower 4, this hex domain is only for fluid flow simulation. And this automatic means that you only have to specify the geometry and 3 parameters, and everything else will be calculated automatically. In our case, we will do a moderate mesh. That means that all the mesh sizes are calculated automatically, and we will use 8 parallel cores to calculate the mesh. And there's a other option where you have to specify the desired mesh order. Here we will use first order. And the difference between first and second order is the way that these elements are approximating the quantities you're looking for. And first order is less compute intensive, needs less computation power, but is only first order. That means you have only a linear interpolation, while second order has a higher computational demand, but it has a higher precision. But for our case, first order, especially since we have only linear deformation, is quite fine. Then we can directly start the simulation, the meshing operation. And now this mesh operation, which takes a lot of computational power, is performed on our cloud. And you will be notified as soon as the mesh is finished. And that is a big advantage of the SimScale platform. If I would now just close this, or even close my, shut down my computer, so operate everything would still work, the operation would still run, and everything you do is saved immediately since it's cloud-based. Because this takes some time, I've already prepared a project including a mesh, so that we use exactly the same settings, but I just started it like half an hour before because this meshing took some time. So let's take a look at the mesh project. We have the same geometrical base. We have TET automatic meshing, first order, moderate, and 8 cores. And here you can see the mesh is loading now. And this is the mesh. And we have all our 5 zones were kept. So we have still, for example, let's take only a look at the femur head. And for example, now you can see this femur head was automatically splitted up into smaller cells, and you can also see that the cell size was automatically adapted. So we have smaller cells here where we have this contact between two parts, and larger cells far away. And the reason for this makes absolutely sense, because only there where we think we will have high changes or high stress, only there we need a fine mesh. And therefore, based on intelligence, the tool automatically refines the mesh there where it thinks you will have high stresses, which you want to resolve. And yes, as I mentioned, we can, for example, also take a look only into this mesh of the bone structure. And here you can see you have different cell sizes for different areas. And we can even make a cut through the mesh and take a look inside the mesh. Therefore, we have to define a cutting plane by giving a reference point. And a normal direction. We can do a preview, so now we will cut really through the bone. We can just apply, and then we can take a look inside the mesh even. So this is a look inside the mesh. Here you can see the cortical bone here in this area. Let me use my pointer, it's maybe easier. So here we have the cortical bone, trabecular bone. We have the stem here, the head, and even the bone marrow. Okay, and that's it. We have created our first numerical mesh, which is, by the way, the biggest step when it's come to create a simulation. And so let's just do a quick wrap up. Yeah. Okay, so we talked about how to create a mesh. So first of all, I showed you how to open a project, and we talked also about the, let's say, main structure of the SimScale user interface. And I showed you how to create a new mesh project, how to add the automatic tetrahedral mesh operation, and we also took a look inside the mesh. And based with this workflow, you can mesh, let's say, 95% of all your CAD models. And advanced topics which we cannot cover today, for example, are CAD cleaning and repair, because you can imagine it was some work to create this CAD model, because it was asked by Alexander how we created this particular model of a bone. We took, let's say, one solid model of a bone from GrabCAD, and then created the inner structure by splitting up the volumes. But you can also create such a geometry of a bone based on a three-dimensional CT scan, for example. There are a lot of opportunities and you can use. And since we're talking about CAD, there was also a question by Rohan. He wants to know which platform can be used to create the CAD models. Basically, you can use every platform you want. For example, we are supporting different Exchange file formats for uploading CAD models to SimScale, so you can use STEP and IGES, as well as STL and BREP. And just because some of you are interested, we have a partner company called Onshape. And they're providing also a free cloud-based CAD system. So with SimScale and Onshape, which are both free, you have all the tools you need to create a simulation and even the CAD model for the simulation. And Onshape is directly connected to SimScale, so you can import a model directly from Onshape or upload it as a STEP, IGES, BREP, or STL file. Okay, then let's keep going on. And since we have finished now our mesh, the next step is to create the actual simulation. And first of all, we click on this new simulation button to create a new simulation. And if we take a look back, we can now use this image to get all the information we need. First of all, we have to give the simulation a name, and let's just call it simulation 1. Later on you should maybe give a more meaningful name. And then we have to decide which simulation type, analysis type we want to run. As you can see, SimScale supports fluid dynamics simulation, solid mechanics simulation, thermostructural simulation, as well as acoustic simulation and particle simulations. And first of all, you have to think what is your problem you want to analyze. In our case, we will use static analysis advanced. Why static? Static because we don't want this, to simulate the whole process of walking, but only a snapshot. And advanced because we need some advanced models and advanced settings to really model the hip joint prosthesis correctly. Click on Save, which will add all items to this project here. And now, by just going through this tree, you will define all necessary settings to create the simulation. And first of all, we have to decide which mesh we want to use. We only have one mesh here, so we will choose the hip joint prosthesis mesh, click on Save, and the mesh will be added to this 3D viewer. Then you have some mandatory things you can add. First of all, you can create, for example, topological entity sets. So you can group different volumes of faces to a face or volume group, but this is not important in our case. The next step here we have to do is creating contacts. And since it's very important to understand why we have to do this, let's talk about the theory of contacts first. And let's take a look. So this is a cut through our 3D model. And here a very important and big difference is that this model is made of different parts. We have at least 5 different solid bodies which are connected. And therefore we not only have to define what are the material property of the single parts and how they are interacting with the environment, we have also to describe how they are interacting, or what is the interaction between the different volumes. And in this case, we're talking about contacts. So let's give a very quick and easy example. If we take a look at this connection between the femur head and the hip joint stem, we have 2 bodies here. And if we would not define a contact, they would be just stick on another, but without any force. But they are connected. So in reality, for example, you have a fixed connection between these 2 parts. And for this you need a contact describes how these 2 parts are interacting, and without the contact here between this and that part, they would not, in the end it could also happen that the parts are intersecting each other. And so you have to define a contact, and a contact is based off a master and a master surfaces and slave surfaces. And you can imagine it like if you do the slave faces are following the master's face surfaces when the body is moving. So imagine this hip joint head would move in this direction, then all these faces are moving in this direction, which would also mean that the faces of the stem, which are touching them, also have to move in this direction. So in the end, for example, a first contact we have to define would be this one. A contact between the inner surface of the whole of the head and the outer surfaces of the shaft of the stem. And like this, we have a contact here. We have a contact here. This contact, so maybe let's write it down. Contact number 1 is between head and stem. Contact number 2 is between trabecular plus marrow. which is here and here, connected to the stem. We have a third contact, which is between the marrow and the trabecula. Sorry. This one here. And we have a contact, finally, between the cortical, trabecular and narrow bone. So we have a last contact here at the outside. Oh no, it became a little bit chaotic. But I hope you basically got it. And we need now to define this contact, as I mentioned, because otherwise the solver or the simulation tool does not know how these parts are interacting. And that is what we will do right now. And first of all, we will start with the first contact, create a new contact, and we'll call this contact head stem contact. It's a bounded contact. It's a bounded contact, which means that the two parts are glued to each other. We could also do a sliding contact where they can move, but this one is a good approximation of reality and easy to set up. We will leave this tolerances as they are with the default value, so that means that if the tolerance for the contact is 1 millimeter, which is fine, and then we have to define master and slave entities. As I mentioned, the master will be our joint head and the slave will be our stem. So let's first of all only take a look at these two parts. And then let's start with our master with the head. So this head is in contact with the stem over these surfaces. And the calling slave surfaces, we can select them here, are these surfaces. We'll add them to slave. And that's it. Now we have defined our first contact between head and stem. And exactly this way you can also create the three other contacts, for example, between stem, all the bones, we can, again, a bounded contact, and this one, for example, is much more work. So the master faces are on the trabecula and the marrow. So sorry guys. And we now would have to select all these inner surfaces which can take some time. Hiding and unhiding features, by the way, will make it much easier for you to manage all this stuff. And here we can see there is still a last. So we can add that here. Then we can select this ones. And so on. And this way you will create also And here you have to be really careful to really take only the right faces. You can add some also here. And then we have all faces we need here. So if you show both of them, all faces are selected, and we do the same for the trabecular and all its outer faces. Right. And then this contact is also done. And exactly the same way we do the two other contacts. The contact between the trabecular and the marrow, which is maybe the easiest one. Because here we only have one contact zone. It's this face for the master for the trabecular, and this face, this one, and then this contact is also done. So the contact between these two parts, and the final and missing contact is the contact between the cortical trabecular marrow. I will not build it because it takes again some time. But I think you got the principle behind it, and for the homework I will provide you with a detailed step-by-step instruction for all faces you have to select in order to create this contacts. And by the way, you have to specify for every contact at minimum one master and one slave entity, and as long as a contact, for example, is not defined completely, it will be red and you cannot start your simulation. So I will just select two faces, because the master will be the trabecular plus the marrow faces. And these outer faces, all of them, and the slaves will be the inner faces. Okay, next we have to define materials. And we have to assign a material model at least to every solid part. And if we take now a look back at our case description, we now have, for every material, a Young's module, the Poisson rate, as well as the density, which is not written here, but I know it, and you can look it up very easily. And so we will start and define the material of the head. So let's call it head, behavior is linear elastic, and we have a Young's module of 210 gigapascal. We have a Poisson ratio of 0.3, and we have a density of 8,800. And we will apply it to the head. We can select it graphically or from the list. Then we will do the same for the stem. Here we have 114 of gigapascal of, and also 0.3 Poisson ratio. and the density is 4,430. And we will add it to the stem. Then we also have the cortical bone material, which is also linear elastic. The only difference is we have only a Young's module of 16 gigapascal and a density of 1,850. And this is very important. You can maybe remember when we talked about stress sealing. I mean, we have 16 gigapascal of Young module for the bone, between 16 and 0.3, and we have between 114 and 210 for this metal alloys used for the prosthesis. This one we will apply here. Then we have the trabecular bone, which has only 1 gigapascal of Young's module and again 0.3 Poisson ratio and a density of 900. We will add it here. And finally, we will add the marrow material. And this is not very stiff, 0.3 gigapascal and 0.45 Poisson ratio by a density of 1,000 kilogram. So it's that's a density like water. And finally, we have to select it. So this marrow. No, sorry, it's not 0. The marrow is here. So marrow. You have really to be careful that you only define one material model for one solid. Okay, now we are nearly done. The last final missing thing is to define how it's interacting with the environment. So first of all, we will for this create boundary conditions. So really, if you have to understand what a boundary condition is, a boundary condition is like describing how the system, our prosthesis, is interacting with its environment. And contrast to that, the context are describing how the subparts are interacting. And first of all, we will fix this hip joint here. It's lower faces. Type is fixed support. Let's call it fixation or fixed. And we will apply it on these two surfaces. And what we will do also is add two loads. First load is, let's call it load 1. It's a force. So you can, there are different possibilities of describing a boundary condition. It can be a force, a pressure, a remote force, a surface load. And here we have just calculated the right vector. So what you basically see here is and so this is a force, and if you take a look, it's like this, going this direction on it, and we have the second force, which is acting in the other direction, and there we also have coordinates which are calculated for the right force vector. So here we're describing in the end the three-dimensional force by three components, just to let you know. And now we're done. The only thing is that we have to change is numerics. We don't have to touch, it's fine, these settings. And the only thing we will change is that we will use 8 cores instead of 4. And we will add additional result control item. Here you can see which solution fields are calculated. And right now you see that we have stress, but the principal stress is missing. So we will add principal stress and now call it principal. And now we will also calculate the principal stress. And that's it. Now we can start the simulation. And for example, if you want to change the material of this simulation, you just can change this parameters. If you want to change the forces, you can change this. And now if you want to create a simulation one, just click on New. Here we get one because this mirror contact is not defined completely, but this is fine since you will define it completely. And then we have the simulation which we can start. Okay, time for a wrap up. So we talked about a lot of things. And one other thing which is very important before we go to the post-processing is to talk a little bit about this principal stress. And I don't want to go too much into details because it's not a fundamental course about engineering, but I think what everybody will understand, you know what stress is. Stress is calculated force applied on the area. And we can have, if in a three-dimensional model, like for example hip joint, if we would make a cut through it, we would have like a lot of different stress at the same time. And the idea of principal stress is that in the end every three-dimensional stress state can be represented by three in a three-dimensional system, so it can be represented by 3 principal stress in each direction. And that allows you to understand three-dimensional stresses without going too much inside the simulation. So it helps you to understand basically how stress is going through your model. And in the end, what it's doing, it says I have 3 components which are orthogonal to each other of stress. I have principal stress 1, 2, and 3, and every of those principal stress is described by amount of the stress and by its direction. And T is describing the amount, and here T, for example, you can describe it with these 3 vectors. Okay, I don't want too much detail. Later you will understand what I mean, hopefully. So what did we talk about? I showed you just in general how to create a new simulation project, how to select the right analysis type, how to assign a mesh. We talked a lot about contact, which is really, really important. So please take really a look at that when it comes to that stage and use the step-by-step tutorial. We defined materials, we defined the boundary condition, and I showed you how to start the simulation. And after the simulation, for sure, I also prepared you something. This is a project including the finished simulation. And so let's take a look into it. And just to let you know, in this case I even made 3 different simulations. I copied the simulation, the initial one, and changed the material parameters so I can compare later on a simulation of 3 different design concepts. So it's every time the same geometry but different materials used. And what we will do right now, so this is the first simulation we did with titanium and cobalt chrome. Here are the contacts I talked about, and this contact here, for example, is now defined completely to make simulation work. And when the simulation is finished, you will get notified, and then you can download the results, or you can to analyze them, or you can the result analysis in your web browser. And for this we switch to the post-processor, and here we can like to perform the post-processing. Okay. And what we will do right now is take a first look inside. So this is our 3D simulation result of the first simulation. And everything we do here right now is also processed in the cloud, so it's incredibly fast compared to your local computer. And yes, first of all, we can change the representation color to different stresses, like Cauchy stress or principal stress or strain, and we can even then change the component we want to visualize. For example, here principal stress has different components. We can even choose which one we want to visualize. We can also turn it to a solid color and even change the opacity of this object. And yes, next thing is that we will now use so-called filters. And first filter we use is the wrap by vector filter, which is visualizing the displacement. So, and let's take a look at the stress, and you can see how this will displace and bend in the load case. And you can use the scale factor to understand it on a qualitative level better. And then you can see this is scaled up to 50 times, but this is how it will, how the prosthesis in the bone will be bended. And so you can see that it's mainly two things happening. First of all, let me do this view. We have a bending like around x-axis, and we also have a bending around y-axis. And what we can also do, for example, is to take a real look inside. And if we add, for example, here now a slice filter, which means we are creating a slice through the simulation. And again, we have to provide the origin as well as the normal. So let's make first a cut in that direction. And then we will do an additional cut in y direction. And so right now we can take a look at it. Just one second. Yes. You have to move the slides now a little bit. Okay, now we can show the visualization of both planes to principal stress. Everybody can. And then, for example, if I now change magnitude to print 1, and print 1 is the main component of the principal stress. So it is the stress which the trabecles will use to orientate. And if we now change this also to principal stress, you can see the principal stress distribution. And then you can really see how the stress is distributed through the assembly. So, and by the way, positive value means compression, therefore negative one is tension. And here you can really see that you have some kind, a little bit of stress branding, stress shielding. So you can see how here, for example, in this area you have compression, here you have tension, and the result is that the bone will become weak in this green-blue area. And the good thing is now we can just change the materials and investigate different hip joints. And there are a lot of other options for visualization you can do, by the way. So maybe one final thing until we make a wrap up. Everything you do here, you can save it. And then if you close SimScale, you can just click here on Saved States and it will recover as a post-processing session. Right. Okay. What do we talked about? First of all, I showed you how to use the different filters. We use the rapid vector filter, slices filter. We change the opacity and save the state. And post-processing is really a very nice thing because it gives you so much freedom and creativity, and there are a lot of advanced things we will not talk about today, but which could be interesting for you. Like you can derivate on additional physical quantities based on the stresses, for example. You can create plots and even do local post-processing on your computer. Okay, great. Then this was our demo so far. And before we have time for question and answers, and I see a lot of questions, let's talk about your homework, which you have to perform in order to qualify for professional training. Okay, and your homework is to redo the simulation I showed you, and not only for one material combination, but you will investigate the effect of different material used for the prosthesis on femur bone. And you will do it for three different material combinations. And for hip joint head and hip joint stem. So, the idea is to compare which of them is the best in regarding minimizing stress shielding. And you can find everything you need to do this homework on our SimScale biomedical workshop page, so simscale.com/biomedical workshop. That's the page where you actually registered. And here now we have different links. One is the step-by-step tutorial, and in this it's a post in our forum where we have really a very detailed tutorial explaining again every step, showing every step, and you can import the project with link in this tutorial. Later on, when you've done your project, it should contain one mesh, 3 simulations. You can submit it using the homework submission form, which you find on our landing page, Biomedical Workshop, and also inside the tutorial you will find it. And there you just, in this form, you later on only have to copy the link of your homework project. There is also a description how to get this, how to share a project, and your email address. Please use the same email address you used to register on SimScale and for the webinar, and we will provide dedicated support for all homeworks. So if you have a problem, just write into our forum and we will help you. And yes, so that's the homework. And now I think there will be some questions. So the mandatory part of the webinar is over. And right now I'm really looking to your questions. There are already some questions I will answer. And if you have one, just write it there. So I have to say thank you very much for joining us today. It was a great pleasure for me to host the session. And I would be so good to see you all again next week to the next session. Please submit your homework. It's a great chance to qualify for a free certification and a free professional training. And you will find the record of this session, by the way, from tomorrow on our YouTube channel and our website. Okay, let's start with the questions. First is by Ali. He wants to know if we can use simulation for a system as a whole, like for blood flow through a dialysis machine. Yes, Ali, that's definitely possible. What it will be a little bit hard, would be to simulate, for example, a full body, because it's also not possible to simulate everything of a full car. But for example, dialysis machine, you can simulate the flow in the machine, how the machine is cooled, the diffusion through the membrane. So simulation basically allows you really to simulate every technical system you want to simulate. Then there is a question by Rohan. And he wants to know, are there possibilities to modify the mesh geometry depending on specific geometry for specific requirement? For example, different mesh on different geometries instead of auto mesh. Okay. Yes, for sure. You can create a mesh manually. For example, let's go back to the meshing. By the way, you can see the meshing operation was finished now from, for example, let's create a new mesh, same base, and add auto hex instead of automatic, parametric, or those local refinements. And then you are able to manually control the cell size on every edge cell, on every volume. Then you can add, for example, refinements for. Okay, I hope this answered your question. If not, let me know. Anand wants to know if should I be expecting any errors or interferences in contacts, or is it 100% reliable? Anand, that's a good question. Let's maybe first of all talk about the simulation I showed you, about the homework. If you follow the instruction of the step-by-step tutorial, it will work 100%. If we are talking about general contact modeling of maybe your own project, most of the time it's also a question of flavor. There are like 100 ways to model contacts, and in the end it's about having a consistent approach. But in general, contacts are not a very, very big deal for such simulation. It can become more complicated, but for most simulations it's not as hard as you think. Then Reshma wants to know if Young's modulus, Poisson ratio, and density are enough to characterize a material like a bone. That's a good question, and maybe therefore let's take a look back at our slides and take a look at the structure again of the bone. Basically, you can only describe material by the 3 parameters if they have a linear elastic behavior, and if they are if it's independent from the direction of the force, the behavior of the material. So a whole bone as a system you cannot model it with just the 3 parameters. But what we've done here is we divided the bone into subsegments which have constant material properties, and there we can use this approach. For sure, it's not 100% exact because it's not linear elastic, but its approximity is good enough for reality. And that's, by the way, a big thing about simulation. It's not about modeling 100% reality, it's about modeling the best approximation you can. Then there is a question by Nina. When making contacts, does it matter which one is the master and which one is the slave? That's again a very good question. And let me explain it that way. Most of the cases not. For example, for all these contacts we made, you could change easily master and slave. The difference between master and slave is that the slave is following the master. So during the simulation, we are calculating, to say it in an easier way, we're calculating the displacement of the master and then how the slave must follow it to make sure the contact is still existing. And that means, for example, if we take a look at this case, it will not make a big difference if this inner surfaces of the head or the outer surfaces of the stem are the master surface. But if, for example, we have a completely different situation, and we just and one part is displacing independent from the other part, then it can have an impact. So you have to choose carefully. And but the rule is really master is the face which is moving and slave the one who's following the master. Okay, then deadline. Good question. Anwar wants to know what is the deadline for the homework. You have 1 week starting from today to submit the homework. So the deadline is next week, Thursday, 1st of September, 12 p.m. Then there is a question and it's about that we are designing only software models or virtual models and how it can help to provide accurate results in testing. That's a very good, let me give you an example. For example, right now we are able to do 3-dimensional scans of vessels. Based on the 3-dimensional scans, we can create a 3-dimensional patient-specific CAD model of his vessel, for example, of his aorta, and then do a simulation to get practical insights. So it's also possible to use Simulate for practical application for therapy on diagnostics. Then there's the next question by Arul Mosi. He wants to know if there are options for user-defined boundary conditions. Yes, they are, but then you have to use, for example, non-linear options. And then Shea wants to know that bone material is mostly nonlinear with composite-like behavior. Is that possible to model in SimScale? Yes, basically we can also model non-isotropic materials or anisotropic materials, as I showed you. But for example, composite models with shell are not possible. But again, this material models we used parameter were based on a paper about a simulation, which was published on a conference, and they did in the end the same approach, and results show that it's good enough. So simulation is really often about simplifying things, making it as simple as possible. And then there's a question by Alexander. You always choose 8 cores. How do you decide that number? That's a good question. Basically, it's Alexander, it's about experience, and the number of cores is important because as more cores you have, as more faster your computation will be. But if you have too many cores, it will not help. You will have like overhead. So you're looking every time for the perfect number of cores which will have the biggest scalability. And 8 cores, 16 cores for the most cases enough. The easiest thing is to start with 4 or 8 cores, and if it's not enough, you will get the error message and you can increase it. And then Ali wants to know how did we calculate the values for the load. That's a good question, and we did it like that. We took a look, we took a paper about the anatomy of walking, and there was a very easy model where they described how these two forces are changing. And then we just calculated them. We calculated the angle and the magnitude, and then we were able to convert this into a vector. Then it's a question by Prasad, and he wants to know how can we decide what axis measurement to take. Can you explain your question a little bit more? I'm not sure what you mean with axis measurement. But maybe if it's about the axis of your simulation, you have axes you can see here, it makes no difference. You can just choose the coordinate system you want, but you then have to make sure that everything is consistent. Okay, guys, since there seems not to be many more questions, thank you very much for joining this webinar. If you get another question in the meantime, just post to the forum. Hope to see you next week. Thank you very much and have a nice evening. Bye.